Okay, thank you to be here for the lecture of today. Today we will see together some variations of Kalman filter. Uh, Please pay attention, I have the digital form of my manuscripts. This let me say, presentation was realized by a couple of students, and sometimes uh, my graphical expressions, let me say, also my graph. No, in general, we will see exactly now the possible scheme is not so clear. It could be that there is something to be corrected, but I will tell you when I see. But at this moment, it seems to be quite good what I am saying directly in this slide. But of course, yeah, I can nevertheless I can improve, or we can improve together if we see some error again, because my calligraphy is not so nice. It could happen. Okay, do you remember last time I told you about this possible exercise in which we have four states. Um, yes, basically we have four, let me say, the physical state to be estimated. Yeah, the physical system is represented or representable, or represented with this x1, x2, x3, x4. And we have here their dynamical expressions. We can see how we have two outputs, something relatively new, but not extremely new, because we will see it does not change much. We can see here that we have an external signal, which we want to estimate. In fact, we can see in this possible representation, in a cascaded representation, the derivative of d equals 0. Do you remember this Gaussian form of a variable? Now, we can see that I split it, this system, into possible systems. As I told you, theoretically, I can split, let me say, as I want. But of course, I would like to say there is a way let me say, to split or to separate the system in a more suitable form. And from this example, we cannot see, let me say, very well exactly, because I didn't start from the physical system. I didn't start from the physical system because the system here is a motor, let me say. Basically, is a synchronous motor. And of course, in complementary for you, it doesn't make much sense to speak about a synchronous motor, because not all students are engineers in a sense. Of course, if I have a physical system, or if I start from a physical system, the best, yeah, I would like to say the most suitable way to split or to cascade the system is to respect, in its representation, of course, is to respect the nature of the subsystem. I mean, in the motor, electrical motor, we have an electrical part and a mechanical one. To represent, and so in the observer, the electrical system and the mechanical system in, let me say, in a separate way, but of course connected each other, because the motor is in a system which transform electrical energy into mechanical one. It seems to be reasonable without mixing the dynamics. Now, if we don't start from, let me say, the physical system, nevertheless, is visible how we can recognize that two systems, how two systems can be split. Why that? Look here. We have here the dynamic of x1 and the dynamic of x2. We can see the input, yeah, but we can see that x4 in the first equation, the second equation, are two variables which are not state in the context of x1 and x2. As states, as in a state, if I consider all four equations. This means an idea is to consider the first two equations as the first, let me say the first representation of the system in the context of the observer, in the context of Kalman filter. And the equation 3 and 4, let me say the second representation. Why that? Because x3 and x4 in these two equations are states. Then the idea is, once we estimate x4 from the second, let me say, representation, we pass the data, or this variable, or the state of the second filter, as a signal here in the first one. And we can see here in the equation 4 that the signal x2 is not, let me say, in the state for the second, we can see basically here, in which I already split. I split. Now, x2 is not a state. As before, x4 is not a state in the filter 1, in the system 1. x2 is the signal for the system 2, which came once we estimated by the first, let me say, Kalman filter. And then we will see now with the scheme, I hope it's correct, the connection between. I do here something more. What I am doing? I am considering here an augmentation, the augmentation of the signal D. The signal D is not disturbance. The signal D is an external signal. In the context of the machine is lowered, the synchro machine. And we consider this as a Gaussian variable. Now, we can see that the augmentation of the variable D in state, because in the original system here, when we have four equations, D is an external signal because we don't have the derivative of D. We don't have the dynamics of D. The augmentation of the dynamic of D with its dynamics here represents a more complex Kalman filter. But please pay attention. I told you many times, now we have the possibility to see it. This augmentation that not represents itself any non-linearity for the system. It doesn't matter if I split or don't split. Does not represent, because we can see that D of T is an isolated signal. This means we can see in the second group of equations, D of T is not multiply, is not appear. D of T appears linearly on the system 2. This means the augmentation not necessarily generates a nonlinearity. Fix the idea. Not necessary. Until now, we have seen that each time in which I am considering an augmentation, we have seen until now, in which I consider, excuse me, an augmentation, we have a nonlinearity. But in this case, I am considering an augmentation, but we don't have it. Why that? Because this variable which I augmented and as a state is isolated, let me say, roughly speaking, let me say, is in the system in a linear form. I add directly. Or this, better to say, physically, the disturbance is a signal, is represented as a signal added to the dynamics form. Let me see if I forgot to say something. Do you remember last time I told a lot? I told a lot about the possibility to judge the excuse me, the observability of a system once I split. Basically, the controllability does not change. The observability does not change. Excuse me if I say controllability, because I came from another lecture and I spoke about the controllability. The controllability is a structural property. Do you remember the example last time? The example last time showed you that we have the same physical structural condition, the same structural condition. If I compare a system, let me say, analyzed, centralized, if I compare the system analyzed, split. Now, here we have to be careful because we have an augmentation. Do you remember I told you augmented, augmented could be that the conditions are not the same. I am speaking about without augmentation. Do you remember last time? I mean, with the same augmentation, better to say, with the same augmentation. What I intend, if I consider the observability of this system here, plus, let me say plus, d derivative equals 0, I have some condition, which at the end must be the same if I consider this condition here and this condition here. Basically, we have 5 equations in both cases. Do you remember last time I told you, apparently, it seems to be that we have different conditions, but basically are the same. Do you remember? I clarified this point here. But it could be that also in this sense, we have sometimes had advantages in one representation, some advantages in the other one. It depends. Do you remember in one case we have the condition u not 0, the derivative of the current not 0. And when I split, we had the condition current on 0 and the derivative of the current on 0. But the current physically came from a voltage. This means the conditions are the same. Let me look. If I forgot to say something, I don't think so. You remember last time the case was an RL circuit in which I augmented R and L, centralized, and which I split the system considering the dynamics, in one case R, then the same dynamics, and L. And we discuss a lot about that. If I discretize equation 1, here we have equation 2, excuse me. No, it's correct, probably I mixed with another file. For Euler means I didn't put here, but now I told you many times. Once I plug in the hypothesis of the approximation of the Forward-Euler, I will have these 2 equations, and now I can put in, let me say, in a normal form, in the sense, in the usual form, no? Explicit form, to be precise, explicit form. Sena, come. Do you help me to switch on the blackboard? I am waiting for you. So we can... okay, but it's better if I stop a little bit the lecture and I help you, because probably, let me see. You have to look for the cable. No, we is in Zoom. We are in Zoom. But nevertheless, come. You joined. Okay. Yeah. Where we were now, I don't remember. Yeah, this is the explicit form. Exactly the explicit form, which we need for the prediction, because we say that everything at step k depends on the states x1 and x2 at the state k at time k depends on everything at time k minus 1. Yeah. Now I would like to excuse me. I hope no error in the scheme. To summarize everything here with the scheme. I hope that everything is okay. Yeah, seems to be correct. Look, we have the system. I told you this is a synchronous system, but in any case, in our case, we have a system with 4 states and an external signal, the disturbance. Here, the disturbance is not indicated. I have to speak with the student that he should put here and then signal D of T, which is disturb, let me say, the system in general, but of course, is directly, let me say, physically in the equation number 4. The equation number 4, if you think a mechanical system, is basically probably you don't have to learn this. It's just an equation which came from a system which from a physical system which not necessarily mechanical an electrical system. It's a system. Act on the equation number 4 in case of the synchronous motor. Here is basically the mechanical system. This could be in this case in a load, no? Torque load. In this case, omega 4 is the angular position, velocity, excuse me, because this last equation is dynamics. Yeah, we can see that U1 and U2 is going after a delay, after it's included a delay. We can see here K minus 1, K minus 1 in KF1. I am measuring from the system X1 and X2, and I will estimate X1 and X2. In fact, I indicated here hat. X1 and X2 is the measured value, and I estimate nevertheless X1 and X2. I can do that. Theoretically, also practically, I would like to say, if we tune well, X1 hat and X2 hat are better than the measured ones. It's better than X1 and X2. The reason is mathematically, you can look at the theorem to remember exactly the name, but there is also a theorem. Once I obtain the estimation of X4. You remember, KF1 is represented here. Of course, in order to work, need the value of X4. X4 is the velocity, if you think about synchronous motors. Yeah. Now, of course, the problem which we have here could be that nevertheless I need let me say time to obtain the estimation of X4 hat, because you can see here we have a 1 divided z, the delay for X1 and X2. I mean, now the equation, the second group of the equations are here. This means to obtain X4, we have a delay. Of course, this is a little bit the price that somehow we can say that we pay in a computational price that we pay. But in general, if we split with this criterion, which basically we respect the physical nature of the system, and we split electrical, and then we consider two systems, electrical and mechanical. Yeah, we can see that X4 is the velocity, or typically the state of the mechanical system. Anyway, we have nevertheless the possibility, because when we split, one reason to split, and then we have basically two different dynamics. and we do two different dynamics, we can compensate. Let me say this possible delay. Yeah, for instance, the mechanical, in this case, the dynamics of the mechanical system. Here I see an error, should be Z. I have to remember to correct, but it's clear. The dynamic of the mechanical system is slower of the mechanic of the Kalman filter. This means the error which I have, including the second Kalman filter, in terms of delay, is not so extremely heavy. It's not so extremely heavy because the variation of y4 over time, over the steps, in our case, is nevertheless relevant with respect, or could be not relevant with respect to the variation, or the dynamics of the state of the Kalman filter KF1, which is an electrical one. And the same here. No? Let me see if I forgot to say something. Could be that I can be a little bit more precise. But of course, this concept to split in two parts, as I introduced exactly now, is valid if we have really, in two parts or in more parts, if you have really two different dynamics in which these possible delays are not so, in this sense, are not so relevant in the sense. For instance, here, as I told you, here x1 and x2 hat is quite fast, and the dynamics of KF2 is quite slow if this is the case, or vice versa. This means we don't have any big influences in the results. Or in general, using the stochastization, using matrix Q, we can nevertheless compensate quite well this delay. Here's the Jacobian of the system here. Look just, first of all, why we have this to 0. I hope no error. Let me see. Now it seems to be correct. Because the state it is x1 and x2. Yeah. And we can see that we don't have here in the first equation x2. This means if I do the derivative of this expression, the x1 with respect to the x2, the x1, to be more precise, to the x1 of k, which is this expression, derivative with respect to the x2 of k minus 1, we don't have here x2 of k minus 1. This means we can justify this 0 here. In the same way here, if you look at the second equation, we don't have x1 of k minus 1. This means if I do this expression, the derivative of this expression with respect to x1 of k minus 1, we have a 0. What about one of them? For instance, this. How I can justify this? Easy. Because we have the derivative of this expression with respect to x1 is 1. The derivative of this expression with respect to x1 is 2 times ts and minus 3. Multiply x4 hat. Why hat? Because the Jacobian here is just the model I did in general, not because otherwise I have to write hat minus here hat. It's the model. Yes. But think about that, including the Kalman filter, here becomes hat minus, here becomes on the right, on the left, everything, this x1 and x2 hat minus. On the right, everything, let me see, roughly speaking, hat must be added. And the Jacobian, in any case, is something included in the Kalman-Friedman. I mean, this could be considered as the model, no? But the Jacobian, okay, I can write the Jacobian also in abstract sense, but just to be more precise, at least in this representation. Okay, if I do the same calculations, or the same approach for the second Kalman-Friedman, let me say, or the second system, I do Forward-Euler. This is the equations. I obtain this expression here. And then we have here a 3 times 3 because we have a 3 states. Because here we also included the augmented. Try to do at home. This could be also a nice exercise, nice project to analyze the nice project, really, to analyze the observability once centralized and then implemented centralized, and once split. The implementation split I will give you. I will update also my study in the next days, and don't worry about it. I will do it. And at this moment, at the end of the semester, I am really extremely busy. Jacobian. Y1, the derivative of this expression with respect to the x3 is 1, because x3 appears linearly in the equation. The derivative of this expression with respect to x4 is ts. The derivative with respect to d, we don't have d. This means 0. Why the last line is 0, 0, 1? It's easy because d of k is equal to d of k minus 1 will becomes a Gaussian variable. And now I have in mind the theorem, do you remember? Excuse me if I come back shortly, the theorem in which we say that the estimation, if the hypothesis of Kalman guarantees is better than the measurements. I mean, here, these inputs could be also considered by the system. Why we don't do practically? Because even though in this case, if I took directly from the system, I don't have a delay. But we pay this price and we have back what? And a better signal. The theorem is Gauss-Marcus theorem. I don't know if you remember, I told you, if you look in the MATLAB, Gauss-Marcus theorem is exactly in MATLAB also in the Google. No? This means if the split is done with criterion, the delay is not a problem. Yeah, 0, 0, 1 is clear, no? Because the derivative of this expression with respect to x1 is 0, the derivative of this expression with respect to x2 is 0. Why now this line here, the line in the middle? Why minus ts? Because we have to calculate the derivative of this expression with respect to x3. We can see here is minus 2 multiply ts, clearly, minus 2 multiply ts. What about this element here? Is the derivative of this expression here with respect to x4. This means 1, because we have here, minus ts multiply 2. Why? Because x4 appear here, minus 2. Why ts here? Because the derivative of this expression with respect to d is 1 multiply ts. Please pay attention. D now becomes a state, an augmented state. Augmented variable in state. Very often we say an augmented state. Now, before going ahead, I have to call. I stop the lecture. We come back in five minutes. Excuse me for this interruption, but in any case, at the end of the semester, excuse me, I will come back. No? Anhalten. Yeah. Yeah, here is basically we have again in a summary what we are doing, which we have the system 0, but Sena, if you want, I switch on this. Are you sure? It's very small. Okay, the system 0 is the original system. Please, this could be a nice project. consider the system 0. You augment the system 0 in considering the derivative, as I told you, which itself does not generate a nonlinearity. But of course, the system is nonlinear because we multiply, for instance, x4 multiply x1. X4 is in a state. We multiply x4 multiply x2, as I told you. Yeah, and we split in two parts. Part 1 and part 2. Here is a little bit in the summary. The input is in a vector, 1 and u2. Here, yeah, I tried a little bit to show the physical system. You know, x1 is in a current, x2 is also in a current. I didn't put here, should be nice if the student had also the second current, I1 and I2. X2 is an estimated variable which we will use for the second state, the second, let me see here, system. But of course, we estimate, let me say, we have many combinations. As I told you, the most used combination is this one, in which we pass both variables. Here it could be I intended to combine to put in the second system and measurements and the estimation. Of course, we can combine, but the most used is exactly here. But of course, it's not prohibited to measure x1 here and to pass x2. But again, in accordance with the Gauss-Markov theorem, this is the most used one. But here is it's not commented, but this is the meaning of this possible notation, which I'm saying because sometimes we use some, how possible to say, some mix, because do you remember, nevertheless, we pay in price here. The price is a delay. It could be that sometimes it's useful to test if we have a better results, just considering one estimated and one measurement. I don't know if it's clear. X1 from the first Kalman filter and X2 directly from the measurements. In any case, we have the measure, we can see here. But both are going just in Kalman filter 1 in this possible configuration. This could be a possibility to check if this combination is somehow improve because of the delay of both. But typically we do something like that. Okay. Here is this, basically is the classical one. X1 and X2 is the input for the second Kalman filter, which came from the Kalman filter 1. Very interesting that X3 we measured together with X1 and X2, but we use just for the Kalman filter 2. And let me conclude, X4, once is estimated, we have to pass back, let me say, in this sense, to the Kalman filter 1. The hat, as I told you, hat, in any case, indicates the estimation. Yeah. I think we can start with the simulation, because here basically is just consideration which Here it's starting from similar system here. I am calculating something related. I don't know if you remember the observability. No? Do you remember the scheme here? I would like to skip this at this moment. I would like to skip because it's the analysis which can be done in the project. I will upload. This means if we are interested to work on this project, we will meet together and I will restart from here to analyze the Jacobian, which we can see here. We can see in this is in a variation. Realism a little bit in a it could be nevertheless interested in a project which look. I don't want to explore from the second Kalman filter, but I want estimate. I want estimate as yeah, and Gaussian variable. Yeah, it's another project. To be basically to be compared here is I didn't clarify because I don't want to put many indication. Was basically the Kalman filter or the structure which I presented until now. Which one? This here, huh? With the feedback. We can see here the feedback without the delay, just to sketch. No? Also here, I didn't put any delay. And interesting to compare, this also complete the project. No? The project is, we can formulate together to analyze the observability with the systems which I told you before, centralized and not centralized. And we can also consider this variation here in which we don't have this feedback here. And so we can evaluate the performance with Simulink. Here we have a little bit the analysis of the of the new systems. I think. Let me see if I see well. I think I don't remember. I have to look because as I told you, this this slide was done by a student. I didn't really check in depth. But during the project, we will see together what I intend. But I think I sketch out at least until here what we can do, and the rest we will see. We will see together. But I think. Anyway, let me now switch in MATLAB. So we can apply exactly. The last part is in a project in the sense you have seen that this slide are basically as a sketch, but until the last the three slides, as I told you, I didn't see any errors. But anyway, do you remember I told you at the beginning that this manuscript, which came from me, was translated in LaTeX by a student, but because of my calligraphy is not good, and sometimes, of course, why we are on a lecture? Because I try to explain what I am flesh out in the slide. I mean, in the slide I cannot write everything which I explain. The last part should be interpreted, but I remember well is in the context of the project. Probably at the end of the lecture, I sketch something which at this moment I don't remember, but we can consider again together. Yeah. Now MATLAB. Just in a second, I will open MATLAB and we will see this example, which in some books or can be written also, can be tandem, sometimes cascaded tandem, as you want. Tandem is a bicycle, no? And we are working together, no? So, but anyway, it doesn't matter the name. Very important if you have to work with these tools, so with the Kalman filter, you want to apply a combination, and as I told you, split if the dynamics are different, if we can recognize two different dynamics. Do you remember last time I insisted? The better way to present the project is to show you the scheme. We have also here some variations in accordance with what I am measuring and what I don't measuring in terms of x1 and x2. Think about our other possible variation. One of them is also to augment it here, the variable. And then, of course, change a little bit. I didn't put here the scheme with the augmentation because we have here another estimation of x4. But of course, and a replication and a redundancy is not something which basically disturb. But of course, try in this sense to do the project if you want and to compare. When eventually we have an advantage with this, when we have an advantage x4. Let me see if I forgot to say something. I don't think so. I'm thinking 1 second, and then we will go to MATLAB. No? In any case, I would like to say that to augment x4 here, we have to say that we have an x4 here, which it seems to be apparently stronger than the x4 augmented here, because x4 here, do you remember, is in a physical variable. Physical means that came from a structural equation. X4 derivative equals 0 is, of course, is something artificial. You remember this word artificial because we consider x4 as a stochastic variable, but it's not because it's deterministic. This means it seems to be that could be a drawback in the sense, but yeah, this x4 here needs to be delayed. I mean, we have need to be, isn't a representation, of course, isn't a presentation, but of course, to calculate x4 hat, we have a delay in the Kalman filter. Of course, if I want to estimate x4 at the end, I will consider this one. The idea is if within a stochastic estimation of x4, we will prove the performance of KF1, and the sense we improve the performance of the whole structure. This could be a possible project to be conceived together, based on the last slide, which I don't want now to go more in depth. Let me think. I forgot to say something. I don't think so. Eventually, with MATLAB, if I forgot to say, I will clarify. Let me open MATLAB. I forgot to do it. Second. I'm opening MATLAB. I will show you these simulations. And then I would like to present the case of next time, and we will see also another time. I don't know when, but in any case, I will upload this weekend everything. No, believe me. I don't know when. It could be, I don't know when. It could be also this week, also in the evening, outside of the, or also next Monday. It could be also next Monday. I have to look on my calendar. Excuse me for this part of the semester. At the end of the semester is really terrible for me, for also for you, I imagine. In particular for me this semester, because we have two projects to be up. To be project, I mean we apply for a European project and a DFG project. And then the deadlines anyway, one is until the 17th February. This means this week and next week we have to work a lot, and then we start after that with the other one. Anyway, therefore, until now we had some meetings. Okay, let me find the file, which you can find. We will find in my study. Let me see if it's here. Tandem, it seems to be this one. I don't know. I'm not sure, no? But let me see. In the meantime, I will tell you what I will present next time. Next time I will present a variation of the Kalman filter using the output. You remember I told you it could be that the model, the nonlinear model, is representable, or we will see this discussed together, representing the output. Excuse me. And that could be an interesting discussion when is suitable, advantages, drawbacks, and so on. I hope that you can see. Not yet, probably. Yeah, okay, now. Let me give you an overview. It seems to be confusing, it is, but I try to. If you want, if you do this project, please improve also this representation. But I try to show you. First of all, it's easy to see that we have two Kalman filters, 1 and 2. I don't know if this is 1 and this is 2, but we have two Kalman filters. This is the second one. We can see X4. We will go in depth later. Here's this Kalman filter 1. All the rest, which we can see here, really confused. But you can put everything in a block, if you want, in subsystem. Is the system. Look, I show you a little bit. No? Then I hope that you can believe me. We have an input signal with a sinusoidal. For instance, two sinusoidal, excuse me, because we have a U1 and U2. Do you remember? Two inputs. Why sinusoidal? I told you using a synchron motor. Probably, I don't know if you remember, Andreas told you about the synchron motor. Anyway, we have a a signal which is AC, alternate current, just to. Even though in this form, it's not necessary, better to, I would like to say, yeah, we just to input in the synchromotor. This means in the synchromotor, in the BQ transformation, this means not necessarily, I mean, steady state, you don't know that, but I tell you, not necessarily in a sinus or cosinus form, but anyway, no, better to say steady state is not the sinusoidal, but just to test the Kalman filter does not matter. The sinus form could be or the pseudosinus in the transient, because he has a particular representation of the synchronous motor, but it does not matter. Look here. Input, let me say U1, this is written here, minus 3 times X1 multiply what? X4, if you look at the system, minus 2 times X1. If you look at the system, if you want, I will look in order to show you a few things, and then you can believe me about it. Let me show you now the slide again. We have seen three times, I remember well, 3 times minus X1 multiplied X4. X4 came from the last equation, but this is the system. No? We simulate the system, the physical system. And do you remember minus X2, X1, excuse me, let me say the short loop. No? Look at this. So we verify this, and you can believe me here. Minus X2 minus 3 times X2. Oh, here is multiply X4. Here, I see. Plus I2. No, I try to remember. Basically, exactly as this. I change X1 with X2. And here we have just 1 X2 instead of 2 multiply X1. Let me show. It's not easy to remember, but I try to do it. The second, let me say, equation is here. We can see here minus 1 X2. Minus 1 X2. Here we have the signal, plus the signal, U2, which is again, whatever signal, to test the Kalman filter, whatever signal. Even though it's not totally valid what I am saying, because you remember, I told you that in nonlinear systems, now it's not the case. I don't remember. No, I don't remember this case. I don't remember. But the case of last time, do you remember the observability depends on the U. This means I cannot say for every input signals, because we have two guarantees. The sufficient conditions say that the determinant must be not zero. This means if I have a sine, cosine, we have to take into consideration that in some points the input is zero. Of course, in some isolated point, it's just mathematically, because an isolated point is a point in terms of time, no? Because we have the sinus in time, which is not observable in an infinite small time. This means mathematically, in some isolated point, the time is not observable. Practically, you don't realize. In 1 nano, in 1 pico, in 1 point, basically, it's in paradox what I am saying, but does not exist. Infinite small time. We cannot understand what is. But mathematically, in this point of time, the system does not is observable. If U appears in the condition as last time. Now, why is not correct to say is observable each input signal? It's not correct because I have to consider if I maintain It's not the case of sine, because if I maintain the signal to 0 for this period of time, the system is not observable. This means the observer is going, let me say, far away from the signal which I want to track. 3 times as before, in this case, x2 multiplied x4. Yeah, here, believe me, is the mechanical system. I don't want to spend energy here. I would like to spend these 10 minutes to discuss the Kalman filter. Just one thing. We can see here the disturbance plus the disturbance in this long equation. Let me say, the equation number 4 is represented here somehow. No? Is a sine function with mean values 10. Okay, let me show you the Kalman filters, and then we will discuss finally the simulation next week, I suppose on Monday. But I will communicate, we will do the last lecture or presentation. If you don't come, it does not matter, but I hope you can come, it should be nice. In any case, the material will upload everything. It is the next time the representation output. Look at this. But this is easy, because now the Kalman filter is always the same, the structure. We have just to adapt the dimensions. We are measuring x1 and x2. This means the R matrix consists of a matrix of 2 times 2. We have a 2 state, also Q is 2 times 2. How we can put this at this moment? I told you a lot about how we can do, but practically, I mean, considering the meaning, considering what changing Q and QR, I told a lot about that. Of course, in the project, very often we do not always manually. We do manually in linear systems, because once tuned, we don't need to retune. In the linear system, we use PSO, neural networks, other intelligent algorithms to tune the Kalman filter. Here, it's always the same. Persistent variable, always old state, old covariance, is the variables which I will reconsider for the next steps. No? We are working with embedded. Now for the initial value, do you remember I don't put the initial value outside. Here, for the covariance, again, initial value of the covariance, because we don't put anything outside. And then the rest is basically I copied from what I told you today in the evening. Here we have the 2 states, which I renamed. The old state which came from the state before, which I renamed x1 and x2 in order to be able to copy exactly the model. This is exactly the model which I presented, in which estimated states is the vector x1 hat minus x2 hat minus. On the right, we have x1 hat without minus and x2 without minus, x2 hat without minus, because of this. Because I passed internally, thanks to the persistent old state variable, the estimated variable or state at the step before. And this here I copied exactly from my slides, let me say, in which everything which you have on the right is the explicit form. Everything at step came as well. Now we can see here the matrix of the measurement is 0, 1, 1, 0. It's strange, but probably the student asked me to change. I would like to put in an exact form. It could be at the end, because we are measuring x1 and x2. Probably the students ask me something. The Jacobian, I copied from my analysis. Do you remember here? It was x4 hat. And then the rest is copied. Of course, please pay attention. two things. First of all, we have two measurements. This means it's a vector of two measurements. We can see that the vector is characterized by semicolon. Why that? Because now the correction, I am doing the correction on both states directly. Let me say directly on both states. Therefore, this semicolon which characterizes or which define or which represent the measurement which I am doing on the two channel, on two dynamics, let me say. The rest is exactly the Kalman-Fitch which we know. Please pay attention. The states, the identity matrix. Here we have the identity matrix 2 times 2, which is multiplied by the estimated covariance matrix. This is the a priori, no? A priori, which is here. But this does not change. Please pay attention. Instead of A in the linear case, you have to put J, no? The Jacobian matrix. Here is quite similar. No changes here. At least structurally, no structurally changes. Let me scroll down quickly. Of course, we have just one state, which we measure. You remember, we measure x3, the position of the model. But we have, we can see 3 states. x3, x4, and d. The rest, persistent. Here we have 3 states, but in any case, the old value, the old covariance, prediction. We can see instead of 2 states as before, we have 3 states, as I told you. This is the vector, which characterized by the 3 dynamics. We can see this semicolon I didn't told you before, but it's intuitive. We have a seen also, no? Characterize the fields. Yes, the vector, but basically the fields is everything which we have here. We measure x3. If you think about the motor, is the rotor position. The Jacobian I commented before. I don't know if you have mistakes here. Let me see. I am checking. I come back to you in 1 second. No, it's correct. It's correct. I copy correctly. And the rest, no changes. Please pay attention here. The 2 important changes to be considered. You have just one measurement, x3, which you can find here. Now we can pass measurement as measurement of the state. Please pay attention here. To simplify, I pass directly x1 and x2, in which x1 and x2, now I clarify in 1 second, is the product of the estimated x1 hat and x2 hat, which I called x1 and x2. But of course, it's the same if I put x1, comma, x2, comma, and I put separately an input. But of course, here we can simplify the notation. The rest does not change anything. Let me clarify this nevertheless, because it could be, I mean, do you remember I estimated from the first Kalman filter x1 and x2. Theoretically, this product should be done internally to pass both internally x1, x2, and to do the product internally. Please pay attention, x1 and x2 are signals for the second Kalman filter. This means it doesn't matter if I do the product out or if I do the product internally. Very important to delay just one. I can delay this and then put separately inside, or I can do the product outside and I can delete once. Okay, let me define TS. I didn't share, but I write TS equals, I don't remember here the value, but let me say 10 up to minus 3. This is the sample time. Let me show you. I don't know, it probably is TS, something like that. I'm not sure about that. Mhm. Seems to be working. I don't know if it's doing correctly, but I hope. Look, for instance, here, let me show you a couple of things. X4. Let me show you really, if you help me to improve X4, no? X4 is here. X4 from the system, which simulate the system, and X4 from the estimation, no? Which came from the second system, which is important because X4 is coming back to the first Kalman filter. It's necessary to have. Necessary. Remember, the possible project included in the other things is to estimate X4 in the first Kalman filter as a Gaussian variable. Let me show you here. This is extremely important, this variable here. Why that? Because we have to estimate quite good, because we need, is an element, a crucial element of this combination, the most important. Of course, in a better tuning can help. Because we can see that the system, the intention, we started from a different value. Because of course, if the value is the same, the Kalman filter will work better. But we don't know exactly for the velocity of the motor, if this is the motor. At the beginning, the Kalman filter seems to be not well oriented, but of course we can tune better. But look, in 1 second, I don't know if this is enough for our application, but it seems to be. Believe me, X4 is estimated. You can believe me, all the rest is estimated. Again, why the X4 is the most important? Again, on the concept. That we can see very well from here. Because it's the unique element in this approach in which we need a feedback. And feedback is always a crucial point. No? I told you also last time. Delay, everything which you already know, which is no. We can see here. Here I have to correct this, not T, but Z. Z means delay. I didn't tell you with this Z. The Z is an important concept in the shifting operator, which is MATLAB is represented in this form here. And yeah, reflect the Z transformation. Reflect the Z transformation. But this is a little bit too much. Okay, I think is everything for today. I hope on Monday to conclude with the last seminar, in which I will tell you about a Kalman filter representation in state, representation in output. We discussed with an interesting mathematical example, but mathematical means for us general. This means no limitation, is not constraint in particular. At least didactically is much better. Why didactical is much better? In complementary, we are not here. I mean, Otherwise, I have to hold the seminar just for engineers. But anyway, sometimes I am telling where the example come from. Let me see if I forgot to say something. I don't think so. Now I am here for you to discuss projects, at the end, Sena, but I have time just until 1:30. Okay. I don't know, probably we have somebody from the audience in Zoom. Let me close the lecture. Thank you to be here. We will see next week, but I will confirm because I am almost sure that we can do a Monday in the evening. In any case, I will record the lecture. No problem if you cannot be present. This week, I promise you, I will upload everything which we did until now. Of course, the lecture. No, the lecture of so last time I will upload. It's already in this presentation. We will see. The presentation which I will upload now is not perfect done, but it's not bad. Thank you. We will see. I will communicate when we will see next time. Thank you.